So far, we have studied the rates of reaction from the qualitative point of view. We have seen how the concentration versus time, reactants decrease with time, the concentration of products increase with time. Now what we want to do is to add some quantitative aspect to what we qualitatively know. So we know that the rate of a reaction, of a chemical reaction, depends on the temperature, concentration, physical state, and catalyst. These are very different factors. We want to, however, understand how these factors affect the rate of the reaction from a quantitative point of view. So the main equation that we will see in kinetics is so-called the rate law. And the rate law includes the temperature, physical state, and catalyst factors into one single constant. This constant is called the kinetic constant, and it includes explicitly the dependence on the concentration. So for a reaction in which A and B react, typically you will see that the rate of the reaction typically, and I say typically because it's not always the case, you will see a dependence on the concentration for each of the reactants. However, that is not always the case. We will call the exponents, and in this case I've used the same exponents as the coefficients of a reaction. However, that is not always the case, so careful. Only in a specific kind of reaction, a reaction that we will call elementary, this is the case. The exponent on the concentration is equal to the coefficient in the reaction. Only in those elementary reactions this is the case. But in general, we will call these exponents order of a reaction. We will say that the order of a reaction is A versus the concentration of A, or is B versus the concentration of B. We will also talk about, so this is partial order. Partial order is the specific order of a specific reactant, and then there is the total order. We have to practice what exactly that means. For example, in this case, we're given two reactions and we're given two rate laws. We are asked to provide the order with respect to each reactant and the overall order, as well as the units of the rate constant. So for equation or reaction A, we say that nitrogen monoxide has order 2, so the rate has an order of 2 with respect to nitrogen monoxide, and has order 1 with respect to oxygen. You don't see it, but of course the exponent on the concentration is 1. The total order is the summation of all the exponents. The total order for this rate law is 2 plus 1, 3. In this case, for the reaction of hydrogen peroxide with iodide, we say that there is order of 1 with respect to hydrogen peroxide and order of 1 again with respect to iodide. In this case, notice that even though there's a coefficient of 3 here, the order is 1. So careful with assuming that the coefficients translate into the exponent on the equation of your rate law. Okay. Also, with respect to the hydronium ions, the order is 0 because it does not show up in the rate law. Therefore, we say that its order is 0. It just contributes as just multiplying by 1. The total order in this second rate law is 1 plus 1, 2. Now, let's talk about what it's saying, the units of the rate constant. The rate always has units of molarity per second. So if we study case A, your rate is a constant times a concentration of NO squared and oxygen 1. In other words, your constant, when multiplied by 3 times molarity, should give molarity divided by second. Therefore, your constant, and I'm moving the molarity to the other side, notice that this one will disappear with one of these ones. Therefore, the units of your constant is 1 over molarity squared divided by second. Often, you will be given the order of your rate law by giving the units of your kinetic constant. Let's practice the other case. For the reaction B, your rate is equal to K, concentration of hydrogen peroxide and iodide. Your rate is always molarity per second, and the constant is molarity times molarity, that's molarity square. Therefore, the units of your kinetic constant will be 1 over molarity second. Okay, hopefully you can figure things out for other kinds of orders. Again, the units of the kinetic constant will give you the order of the reaction. Let's practice some more as we try to understand how we can measure the order of a reaction and the value of the kinetic constant. This method is called the initial rate method, and it's based on using different experiments. One sets up different experiments with different initial concentrations, and one measures the initial rate. So for this reaction, nitrogen monoxide reacting with oxygen, one sets up this first experiment, and now one compares it with the second experiment. The difference between the first experiment and the second experiment is that we doubled the initial concentration of oxygen, and then we measure again the initial rate. What happened to the initial rate? Well, it got multiplied by 2. This means that the rate law for this reaction has to be a constant times the concentration of oxygen. When you double the concentration of oxygen, the rate gets doubled. This means that the exponent on the oxygen is 1. Okay, if it were something else, you would see a different factor multiplying the whole rate. So, and that will be clear in the third experiment. Comparing experiment 1 and experiment 2, we left this one constant for oxygen. However, we doubled the concentration of nitrogen monoxide. What happens when you double the concentration of nitrogen monoxide? The rate gets multiplied by a factor of 2. Now, the order of nitrogen monoxide cannot be 1. If you multiply this by 2, let me put it down here. If you multiply this by 2 and the rate gets multiplied by 4, it means that there has to be a factor here, that 2 to the 2 is 4, that gets the rate 4. We have been able, just with 3 experiments, to identify the order of the reaction with respect to each of the components. Again, in this case, it's a coincidence. It's not necessarily a coincidence, but it cannot be extrapolated to other cases that the coefficients of the reaction correspond to the order of each of those reactants. So careful here, it may not always be the case. So let's practice one last time and see if that makes some sense. You're given a reaction, and we do not know what the order with respect to concentrations of A and B is. However, we set up 3 different experiments with 3 different initial concentrations. These are initial concentrations, and we measure the initial rate. We say the initial rate because we have to make sure that the concentrations are the ones that we put in. Of course, later on the rate will decrease and the concentrations are different. So if we compare a trial 1 with 2, we have doubled this, keeping B the same. What has happened? It has happened that the initial rate is multiplied by 2. Therefore, we can say that my rate has a linear dependence with A, because when you double concentration of A, the rate gets doubled. Now let's see what happens if we double concentration of B, keeping A constant. Again, when we double the concentration of B, the rate doubles. So the only option that we can see is that the order with respect to A and B is 1 for each case, a total order of 2. Okay, so this would be the solution. Hopefully this makes sense. One can also set up these experiments to find the rate constant, that just you use 2 equations with 2 unknowns, and that should allow you to find the kinetic constant.